Save that for the next module. How's that?
Okay.
All right.
Okay, thank you, JJ. So I'll try to be not too long to leave you guys at train time to talk about your experience, your cases. So this module is about HVAC. Even though it says HVAC, it's really about ventilation because HVAC is kind of larger, the larger family. We're going to talk mostly about ventilation. A lot of it is about optimization, which actually kind of overlaps with the recommissioning piece that we just saw. But in this case, I will expand to say that we're looking at measures that will have some capital costs, maybe not like extreme capital costs where you would rip out entire systems and replace them. That would be major overhauls. But we'll talk about things that can be done at this, kind of intermediate cost where it's not, those really large overhauls, but can still be done within like a 3 to 5 year payback. So HVAC opportunities, and I'm talking about what I call the frontline system. Those are the systems that really dictate most of your comfort condition because they're the one that provide the heating and the cooling in large part to your spaces, and obviously the ventilation. And when I say ventilation, that's fresh air ventilation, as well as the air changeover that's required in the healthcare. So they are very critical in establishing the comfort condition, obviously the energy usage, and you have to obviously optimize the way you use the equipment in place. Most places will not, like I said, have budgets to replace the entire system, so you can try to tweak what you have through controls, EBCX, as it says on the first bullet point here, but you can go further than that and try to implement variable speed drives with some VAV boxes if you have, and I'll talk about that in some case study that I've worked on. Obviously involve some behavior because occupants may have an impact on some of the terminal units in the system. And there's things you try to eliminate, such as simultaneous heating and cooling, which is really a recommissioning measure. There's example also, there's a lot of humidification going in the healthcare buildings. And depending how your humidification system is set up, it can actually, and I've got example of that, have simultaneous cooling and humidification. So you kind of are combating yourself there. So those are all items that you want to take a good look at. And then there's the other measures, such as demand control ventilation and heat recovery. And here we're not talking about chiller heat recovery. I know there's somebody, I think, from Vancouver or Edmonton that is right now using chiller heat recovery. That will be discussed in the next module. Here we're talking about outside air heat recovery. Demand control ventilation, it depends. You cannot use it in many of the systems. If you have type 1 and type 2 spaces, usually you'll leave DCV, demand control, you leave that alone. That will be for type 3 spaces. For those of you who are not used to the type of spaces, type 3 is more the ancillary spaces, the administration areas, stuff like that. You obviously will try to optimize your airside free cooling. And again, you got to be very careful. Airside free cooling, if you have a lot of humidification, sometimes you better try to use water side free cooling. So there's things that can be done. And if you have a heat recovery chiller, we'll talk about that later also, airside free cooling may not be the thing for you. So those are all optimization strategy that you need to look at. But in order to look at that properly, you need to make sure you understand your HVAC system. Don't purely and solely rely on your contractors, on your engineers. I've seen engineers install heat wheels and demand control ventilation on systems that should never have those. They were not suited for that, but they kind of use this blanket recipe of putting heat recovery everywhere. On the 10%, 15% outside air VAV system, there is no need to have heat recovery in most places in our climate. So you got to be very careful. Make sure you understand the system or your team understand the systems so that if somebody comes to you with measures for the HVAC system, you're well equipped to judge if it's a valid measure or if it's not. And you do a review system by system again, you need to know the proper requirement for that system, what humidity level it needs to keep, what fresh air level it needs to keep. Those have to be known. Requirements, they do change, and JJ will talk a bit about the CSA standards. So you got to be careful to update those CFR on a system by system or space by space basis. I've got an example here of a typical HVAC system that would probably serve very often what I call the type 3 spaces, the administrative areas. You may have it also in other spaces, but it's very common in those type of spaces. It's a VAV system where you have what I call the cold deck. So you got your supply fan. I'm going to go here with my drawing tool. So you got your supply fan and you've got your supply deck. We call that a cold deck because this system is not a heating system. When I told you some systems don't really deserve to have heat recovery, well, this system, in many instances, not all the time, does not require heat recovery because it's what we call a cold deck system. This fan will blow air that goes to VAV boxes that will modulate based on the space temperature, as a lot of you, I'm sure, already know. But you will supply air between 13 and 18 degrees, typically. But you will, in an administrative area, have 85% return. I mean, it should be about 30%, but in practice, we often see only 10 to 15% fresh air, so 85 to 90% return. That mixed air temperature right here is already warm enough that if you warm it any further, it will be too hot in the supply. So even if you have a heat recovery wheel right here, it will not kick in because your mixed air is already warm enough. Now, for any of you that have a heat recovery chiller, you could decide to put here a heat recovery wheel. You will overheat your mixed air. You'll use your cooling coil to recool that air, and that will transfer heat to your condenser that will then serve to heat your building. So that's why I say you need to know how your systems work to see if a measure is appropriate for your system. So in this instance, DCV and heat recovery, and DCV is demand control ventilation, would be something you would have to look at twice before installing. If your BAS vendor comes in, says you have a VAV, I'm going to put CO2 sensors in every room because you can't use a return sensor on a VAV system, that is not acceptable. You have to have zone level sensors. That's a lot of maintenance, and it will likely save you very little on a regular VAV. If you have a high percentage air VAV, yes, that becomes interesting when it's possible. You have to, again, know your regulation. Are you subject to CSA Z713.2? If so, well, DCV is restricted to just a few spaces. So that's what you need to know on your HVAC system. And there's a few other examples here that I'll go quickly. If you have a dual duct system, a lot of older, larger buildings had those. I've done a few audits and recommissioning in the Gaspé Peninsula hospitals, and they had dual duct systems. They are very complex to optimize their controls because you have one fresh air intake when you have a single fan dual duct. It will supply the same air to a hot deck, which supply your heating, and a cold deck. How do you optimize the amount of fresh air you get in here is very difficult. If you want to do free cooling, you will dump a lot of cold air in your hot deck. It will cost you a fortune. So the best way is to have a water side economizer, use your cooling tower to do your free cooling. If you don't have one, it is sometimes worth it to install a plate exchanger and do that kind of free cooling. So again, knowing your HVAC system is critical. Once you know your HVAC system, you also need to know what's your air changes. If you want to meet the CSA standard, do I have my 6 air change in my office spaces? Do I have my 20 air change in my operating room? What is my outside air compared to my total air? Most of you are familiar with the standard. You know how those systems are defined. We call them, for example, a 2.6 or a 6.20. The first number is the number of fresh air change you need. The second number is the number of total ventilation, total air changes in the space. So you need to have that in your CFR, make sure your system is providing what is needed, which becomes recommissioning basically, and then look at other measures such as, like I said, do I need heat recovery in this one? Can I install DCV in this one? So you need to know the type of system in order to judge if the measure is applicable. Another one that's very common, it's a makeup air unit. It's 100% fresh air. Older design in healthcare had a lot of makeup air units for, let's say, operating room or even for patient care section where all you had was a makeup air unit feeding corridors or feeding the actual spaces, the rooms themselves. Those are perfect for heat recovery. They are the best candidate for heat recovery when it's possible, obviously. If you have many exhausts, that becomes impossible. You have to have centralized exhaust. When you have a system like that, you can actually, if you have a heat recovery chiller, you can cool your exhaust with your return chilled water line and capture that heat in your chilled water, which will then dump it to your condenser that can then be used to heat the building. So you do indirect heat recovery. Makeup air units can be good for that, or any exhaust that you have can be good for that. Single zone system, you'll have many single zone systems. Again, they're very good candidates for demand control ventilation when it's possible, and for heat recovery because they only serve one zone, so they can go hot. They can be a hot deck. You can, when there's a heating call, supply warm air to that space, which allows your heat wheel or whatever recovery device to kick in. So again, just highlight how important the type of HVAC you have and to know what the CFR, the requirements of that space are in order to select properly your system. Be very wary of those standardized measures that somebody comes say, hey, we're doing that everywhere. That doesn't mean it should be there. A heat recovery wheel that is not recovering unless you have a bypass will cost you money. It will have a 1-inch delta P, 1-inch pressure drop, which you will pay at all time when the fan is operating. So always look at the entire picture. There's a helpful hint on the operation and maintenance.
Michelle,
yes.
Can I just jump in on your first item here on the helpful hint? Start tracking hot and cold calls and solutions, discuss results, staff meetings. Katie Cowan, who's going to be presenting on behavior, has some experience with exactly that. That became one of their interventions at one of the projects she worked on and had some amazing results. Katie, I think you're going to speak to that one in the final in our module 14, are you not?
I have incredible story to tell you, and you'll all have to wait till module 14 to hear it.
There we go.
Something else I can tell of the hot and cold calls. When I do a recommissioning, I do a kind of a heat map of the cold and hot calls to know where is their concentration in a section. And there's buildings where we use the heat map based on when the hot and cold calls are well tracked and you can identify where they are, you can target that section. Because right now we talked about the ventilation units, which are the main air handler. But when we talk about ventilation, we also have to talk about the diffusers, how the air gets into the space. And when we're talking about hot and cold calls, those diffusers, they often become really the problematic system. And the operator may just go there and do some adjustments, but the problem is elsewhere. Maybe the diffuser is not well aligned, it's against a wall, the air is just dropping down that wall. And then the operator says, oh, that person's always complaining. I can never be satisfied. That is possible, but it's also possible that it's due to the distribution of the air. So having the hot and cold calls properly tracked, like I said, is really important. And that's not in the slide. You should forbid the use of infrared guns for hot and cold call. Infrared guns, they're very nice. The operators like them, but they are not good for hot and cold calls. Those devices, those instruments are not made to measure air temperature. They measure surface temperature. You have to have the proper emissivity. It's very imprecise. So you should always have a handheld thermistor-based temperature sensor when you measure hot and cold calls if you want to measure what the actual temperature in the space is, not an infrared gun.
Can I say one other quick thing? Sorry, Michelle. I just a little teaser for Module 14. Just very fast. One of the things that we found to be so successful with our operators was having them flip their mindset from looking at those calls as complaints to looking at them as data. Like you said, to map and track where those calls were coming from so they could add them up and find root cause solutions. And when they were able to flip from this is a burden to this is fantastic because it's going to help me solve more problems, we were off to the races. Thank you.
Yeah, I totally agree. For me, when I get to a building that has a good log of the hot and cold call, I'm like, wow, this is like gold. It's really good information. So yeah, that's a very good point. Thank you. The other hint that I want to, and that's a myth sometimes that I always hear, is that temperature setbacks. So if you've got an electrically heated building and you do a temperature setback in the section where it's not obviously 24/7 occupation, so it has to be unoccupied, you will be able to save. People say, hey, it doesn't save. Setback always save energy. It can kill you on demand, and you will pay more at the end of the month, but it saves energy. If you've got a gas heated building and you can set back a portion of it, if done properly, I'm not saying setting back crazy and then, you know, people freeze in the morning and or after a weekend, but doing it properly is guaranteed to save energy. I've had so much arguments with operators. They say, hey, setback doesn't save energy because my boiler just runs for an hour straight when I come back. Well, it did not run very much when you were not there. That's why it's running an hour straight now. So just in case anybody doubts, setbacks always save energy, but be very careful how you do it. A lot of hospitals can schedule system for, like I said, type 2 spaces, type 3 spaces. They can be set back and they can be scheduled. You can shut off those sections. When it's a type 2 space, you have to monitor the space temperature so it stays within certain parameters, but it can be done and it should be done. I'm not talking about COVID period. So that during COVID, there are specific ways of running the system. For type 3 spaces, if you do schedule it off, you can schedule it off. You need to flush the space with 3 air changes before occupancy. You can decide to do that half after occupancy and half before, but ASHRAE's guideline for COVID-19 operation is 3 fresh air change if you schedule a system off. And obviously, you ensure good maintenance. Hospitals typically have MERV 8 pre-filters and MERV 13 or 14 filters, plus sometimes HEPA filters, depending on the spaces. Well, all those filters have specific times to be changed and to be actually verified. If you've got 3 sets of filters, the pre-filter has to be checked every week. Secondary filter is monthly. So there's schedules like that. Make sure that is done. Filters that have too great of a delta P should be changed, even though on a constant flow system. Stephen can talk about that. A high delta P on a constant flow system saves fan energy, but is really bad on your total airflow. You will not get your air changes if you do that.
So Michelle, I'm just going to give you like a 5-minute warning, and just to point out that
I'm almost done. I'll be able to pass the puck to train. Just a couple of slides on the CSA standard, and I will actually ask JJ on the third one to talk about it. So the CSA standard is usually used in the healthcare sector. I know it's not everybody's not all from Canada here, but it's our standard for fresh air. And like I said, it expresses the systems in those terms. 620, I would mean 6 fresh air change per hour over a total of 620 recirculated airflow. So, operating room used sometimes to be 100% fresh air, let's say a 15-15 system or a 10-10 system. Nowadays, with the latest standard, you can have operating rooms that are 620. That means they recirculate a good portion of the air. Obviously, they have high filtration requirements, but they are not 100% fresh air. So if you are running 100% fresh air, you're using an older version of what the CSA standard was. And if it's possible, and you can go to something like a 620, then you can actually achieve some significant savings. And like I said before, CSA also allows you to go to lower volumes, and actually you can actually stop for some spaces the system. So you have to be always on top of that. Where can I stop it? When I stop it, do I have to monitor the space or not? So make sure you're aware of that. JJ, I think I'm going to pass it to you right here for the last two slides.
Yeah, I just threw this slide in there, just food for thought, the challenging the current CSA standards. I think we talked about engineered infection control in our lighting section. And, more and more, that type of technology is going to impact on what we see as normal or, as far as CSA standards go. So, for instance, the current ORs systems are high volumes or laminar flow, so you create that air curtain around the OR table. You wonder in the future with UVC and ozonated water technologies if, in fact, that surgical site will be allowed to have lower volumes of air with UVC and ozonated water misting happening at the same time as the surgery to cut down on surgical site infections. We're using typically now UV systems in HVACs, on our drip pans or coils, and in some cases along the ductwork. And so you'll see, I'm sure, impact on, the need for water treatment and biocides and filter systems will change as well. The constant UV sanitation in patient treatment rooms, it was mentioned by Krishan in the lighting section that the UVC lights that you can install and they work constantly in patient rooms and no harm to the patient or staff. And then, of course, you also have copper touch surfaces. So I can see in future that CSA will be challenged. And in fact, in some cases, in some of the ORs, we're now seeing ORs with the COVID outbreak being changed over to negative pressure. And that's being done in a few areas. I believe that Winnipeg is doing some work in that regard. And so I think CSA is going to have to become more flexible and to start writing standards around these new engineered infection control systems.
And I think that's a bit of a challenge because they're not known to be a fast and nimble organization.
No, they aren't.
It's often a 5 to 10 year process for these things because people want to be careful and they want to be certain, and because they know they're giving direction to the broader marketplace.
Yeah, absolutely. Good point, Jeff.
Okay. So I'm going to skip the activities. We don't have time for that. You'll have them in the slides. And if you have any questions, you'll have our email. There's a couple of case studies, but I think I will actually go directly to the people at Train and give you the floor here.
Okay, well, thanks very much. I'm going to ask Matt Sharp to lead us through one, perhaps two examples. Do we have, how much time do we have, JJ? I've got 2:28 on our local clock here.
How's 10 minutes sound?
Okay.
If you have any slides, I can give you the ability to project slides if you like, Jeff.
I don't believe we have slides. So,
okay.
So just our smiling faces. So.
That works.
Matt, do you want to take it from here?
Yeah, sure. Well, I can talk to a couple of examples. So as Jeff mentioned, I've been with Train for 5 years now, and prior to that, I was in a facility role in a large downtown hospital here in the Greater Toronto area. Um, well, to be exact, it was sick kids, so very specialized place, very large place, very well known, very unique place as well because when you look at the space and the amount of beds versus the total square footage and kind of the use of space, it's very different than what I would call a general hospital. Say I live in Newmarket, so if I compare sick kids to South Lake here, probably comparable bed count, but probably about 3 times the square footage at sick kids. I've also, in the past 5 years, we've worked a lot. We worked in a few hospitals as Train. We've specifically done a lot of work for Brantford General. We've done quite a bit of work for Armpire General, so I can speak to a few examples from them as well. I guess the first example from Brantford General, I think one of the largest opportunities around HVAC optimization is really using the systems for the space they serve, and design engineers, they're risk adverse people. They tend to install systems that are going to kind of work and work under all circumstances and work best on the peak heating degree day and the peak cooling degree day. But the reality is those days only occur about 6% of the time, and you're left with all this other time in between. As well, hospitals are living spaces. We've heard that time and time again. People think of hospitals, they're 24/7 operations. Reality is maybe 30-40% of the space is 24/7, and there's a whole lot of space that's clinical space, a whole lot of space that's really kind of normal operations, or maybe used during the day quite heavy, used a little bit in the evening, and then is empty after hours. So at Brantford General, we looked at the building. We looked. There was about 30 air handlers, and we signaled out about a half a dozen air handlers that served spaces that they were kind of mixed spaces where they had some occupied space after hours, but they served spaces where very large spaces like the shipping and receiving area, where the space was empty after hours. So we looked at these air handlers. We put in VFDs and we put in zone dampers, both on the supply and on the return side, to limit the air after hours to the spaces that were not not occupied. There were spaces that we were able to shut down at say 6 o'clock. There were other spaces that we were able to shut down after 11 p.m. Depending on the use. And really, it's kind of around that separation of, okay, what's 24/7 versus what's 8 hours, 9 hours a day, 5 days a week, or 6 days a week. So that was quite successful. One thing to bear in mind is, if you depending on the space, if it's the MDR or a critical area of the hospital, if you install a damper on a duct system and you influence the supply, you got to take a look at the return side as well. So you're not creating the space, putting the space after hours into a negative condition. Sometimes we focus on the supply. We don't look at the return side all the time.
Matt, can I just ask a clarifying question for everybody? So if I recall, this system was the primary source for heating and cooling for the spaces, right? or was it
Yeah,
just cooling?
definitely primary source for cooling, and I would say the split source for heating, where you'd have your air being heated by the air handler with reheat coils, and then the skin of the building being heated with radiation.
Okay,
So kind of a split duty on the heating, but 100% the cooling. So that's a real good point. If I pick on the the warehousing area, they had some radiation around the skin of the building. So after hours, we didn't have to be too worried about that space temperature dropping too much. My colleague spoke about setback. You'll always save energy if you can set the temperature back. Having said that, you don't want to go too deep because you're storing goods in that area and things. So the radiation was able to maintain 68, 67 degrees after hours. The flip side of that is in the summertime, you shut back, you limit your air after hours. Say you close your air off after 11 p.m. Your cooling capacity goes away, so you've got to watch and make sure the space temperature doesn't rise too much. But after 11 o'clock, usually your cooling loads kind of go away as well, especially if the space is unoccupied and you shut your lights off and there's no people in the space. Does that answer your question, Jeff?
Yeah, and so I guess I was thinking, when you mentioned a variable speed drive there, many times variable speed drives are applied to cooling only systems, but this is a case where I think with the variable speed drive element was just a sleek way of getting the speed down for after hours, as opposed to every hour or every minute of every day adjusting the volume.
Right.
When you start shutting off dampers and
right. And for those that have been around the HVAC industry, say in the large commercial office space, VAC systems are used all the time, and the air responds in demand of the thermal requirements of the space. You slow the air down on a call for less cooling, and you speed up on a call for cooling. Well, we don't do that in healthcare. Healthcare, it's 6 air changes per hour in patient rooms. It's 20 air changes in ORs. It's everything in between for other type of spaces. But this particular system served the MDR, and it served the warehouse space. The MDR we kept at its required air changes all the time, and the warehouse space we limited the air after hours. So we did not use the VFD to throttle, so to speak, during occupied periods. Does that answer your question? I think so.
Yeah.
The other application I can speak of is when I was at Sick Kids. I arrived there in late 2013. The facility manager that reported up to me, he was already well underway on an OR optimization project. There was about a dozen ORs, 2 fan systems, or roughly, this was it's going back 7 years ago, so please forgive me if I forget the CFMs and the capacity, but there was 12 ORs, there was 2 fan systems. I believe they were 24,000 CFM a piece, but I could be off on that number. 100% outdoor air. We put dampers to limit the airflow to 6 air changes when the ORs were not in use. And a couple different ways you can trigger that. In this case, we elected to do it with a manual button. the OR manager would have some control of, so she could bring the OR back in up to 20 air changes well prior to a procedure. They wanted that kind of flexibility and that kind of command of the system, that they could bring it up well prior to a procedure taking place. That's something, that's something that the code allows you to do. Having said that, when you undertake a project like this, I did a presentation about this very subject in it was at Chess Ottawa conference in 2015, and I had a lot of questions around, well, how'd you get the internal stakeholders to agree to reduced airflow after hours and things? Did you have problems? And yes, we did. I mean, it was something that a lot of people had to get involved. A lot of people had to approve. There was a little bit of uncertainty. We had to kind of test the waters and oh, okay, we won't go to 6. We won't go from 20 to 6. We'll go from 20 to 12. We'll try that. And there was a lot of concern about the space temperature drifting. We didn't touch the space temperature at all. We restricted the airflow after hours, but we held the space temperature. So if the space started to warm up, we would increase the airflow to match the thermal requirements after hours. We didn't want to mess around too much with the space temp, but that is something, if you can get the right people nodding, and you can implement demand control ventilation after hours in an OR, that's something that's going to save a lot of money. ORs are big energy users in healthcare.
Okay.
Okay, so that's all I got. It's kind of, in my mind, it's probably the two ends of the spectrum. You're talking about the shipping, receiving, stores area in a hospital, which is probably one of the less sensitive areas in a hospital, right up to the ORs, which are obviously paramount to the hospital's operation. Any questions? Any comments?
Okay, none being heard. Thank you for those examples, Matthew and Jeff. Moving into our next section, we have a 3:30 stop time today. That was according to our schedule. So does everybody want to take a 3-minute break, and then we'll start at 2:45, or just carry on?
I think a break should be great.
All right. Actually, I have one question from Davude. Would there be a chance to touch on pressure-dependent or pressure-independent methods of ventilation for our systems? Some of the existing ORs boxes for some hospitals are at the end of life, and a good decision up front can save a lot of headache down the line.
Do you want, JJ, do you want me to comment, or Michelle, do you want to comment?
You go ahead, and I'll see if you. I was going to say pressure independent, but I'll let you take the bat first.
Sure. Yeah. So, I mean, in healthcare, you typically have your constant air boxes that maintain a specific airflow. I guess as you start varying air and the system becomes more dynamic, your pressure dependent boxes are kind of they're a better way to go. And I think of when I was at Sick Kids, they opened a new laboratory building, and as everybody knows, laboratory air in, air out is so crucial. You know, there you have your boxes that control the air in, and then you have your air valves that basically control the air out. So I would you know, if you're replacing, I would go with the premium when all applicable, when all possible.
Okay, good advice.
That, Michael, do you want to, any comments or?
No, I agree. And by the way, I was on mute before. I just wanted to let you know the example you gave about isolation damper and VFD. That's exactly the same example that I implemented in the Rimouski Hospital that will be in the slide deck. And the way I did not actually have too much problem with convincing the operating team, because I was working directly for the operation manager with one of his tech, and we identified, it's very, very similar to what you did. The spaces, making sure that spaces that were not 24/7 would be, you know, isolated at night, checking that we maintain the pressures, the proper pressures in the other adjacent zones. And we did MNV on that, individual MNV, and I mean, we saved like 15% electricity. I mean, not just with that, but there was other projects, and there was actually no problem at all. And if they're not variable volume system, like Jeff said, those are not variable volume system, they're constant volume, and we just isolate a portion because they are no longer serving just 24/7. I'd say that would be almost in every hospital a measure that can be applied, because most hospitals have now sections that are no longer 24/7 and they are served by 24/7 systems.
All right.
I like your term better than a VAV system, because they're not really VAV systems.
No, they're not. No, they're not.
Okay, we got time. Yep.
Okay.
All right. Thanks, Matt.
Well, thanks, JJ, for having us.
Thank you, Jeff.
And thanks to both.
Jeff, what was that? Sorry, Stephen.
I said thanks to Abood. He's had a lot of great questions today. So.
Oh yeah. Jeff, do you have somebody to introduce for the chiller section?
Yeah, I'm not sure that if he's on. I haven't checked the attendee list right now, but hopefully David Titus is on or is soon to be on. Oh yeah, he is on. Great. Hi, Dave. Dave's up in Ottawa. He's been with Train for a number of years as well, and he's an account manager for Train, and very successful one actually. Dave gets he understands systems really well. He's great with customers and has helped them solve a lot of their problems in their respective buildings. And I think later on in this session he'll give his perspective on a solution that was provided to what we'll call it a mid-northern hospital here in Ontario when it came to the cooling side of things. So we'll save that for a few minutes from now, I guess.
Well, 3:15.
3:15 it is. Deal.
Okay.
So, we're not stopping. We're going straight ahead.
Yeah. Throw your slides up there, and we're good to go, Michelle.
Okay. Oops.